Okay, so welcome to my first talk. I will talk about my recent joint work with Tsachik about the relation between the volume and injectivity radius in higher rank locally symmetric spaces. So the topic of this talk, this will be a series of 2 talks, about 20 minutes each. The topic is infinite volume versus infinite injectivity radius. So in the first talk, I'll try to state the results. And compare them with normal subgroup theorem and other classical theorems. So let me just maybe put it here in writing that this is joint work with Tsachik. And you can find the relevant preprint on archive. And as said, we have just one preprint together, so you'll find it if you type in our names. Yeah, so I'll talk about main results and maybe some ideas in relation with normal subgroup theorem. Depending how it goes, in the second talk, I'll mention some, I'll describe some arguments that enter the proof. In particular, the heavy usage of stationary random subgroups. Okay, so what is our setting? So let's just start by talking about injectivity radius. Injectivity, too many T's. Injectivity radius. So G will be a semi-simple group. X will be a symmetric space associated with G. So for now, we don't have to assume that G is a higher rank. We'll do this later. So gamma will be a discrete subgroup of G. So whenever we have such a group gamma, we can look at the quotient of X by gamma, and this is a locally symmetric space. So a good example to keep in mind is when G is SL to R, then the symmetric space is hyperbolic plane, which is the quotient of SL to R over SO2. And as our group gamma, we can choose, for example, a lattice SL to Z. Right, then this quotient is a very well known object. This is the modular curve. Okay, I guess since this is a part of the conference about local symmetric spaces, you all know this example. So just to set up the notation, I will remind you what is the injectivity radius at the point. So if P is a point in the local symmetric space, X mod gamma, so P is right coset of gamma and left coset of K. So left coset of gamma and right coset of K. Then I define the injectivity radius of this space X mod gamma at the point P as the supremum over all R. So R non-negative such that the ball, let's denote a ball of radius r around point P as BPR, this ball lifts isometrically to the universal cover, so to X. So it's always good to draw a picture. For example, if my space looks like this, so the only locally symmetric space we can reasonably draw is the hyperbolic surface, so that's what I'm drawing. So in this case, the injectivity radius will be just the radius of a largest ball that you can take around this point P, such that this ball does not overlap itself. Okay, so that's the injectivity radius. It measures like how far must we go in the local symmetric space to see that we return to the same points. Now, after we define the injectivity radius, I can define for you the thin and the thick part of the symmetric space. So a thin part will be denoted as the space index less than r. This is the set of points x omega p in gamma mod x, such that injectivity radius at p is less than r. So typically the parts of the space that have small injectivity radius, at least for hyperbolic spaces, are formed of colors around short geodesics. So typically it will look somewhat like this. Okay. Cool. So we have defined the injectivity radius, and now I can state the main results that we proved with Tsachik. So let's call it theorem A. So theorem says that if X is an irreducible higher rank symmetric space, then every locally symmetric space which has uniformly bounded injectivity radius must in fact have a finite volume. So I can state like this: if X is an irreducible higher rank symmetric space, then the following conditions are equivalent. So we have two. One, this space X mod gamma has uniformly bounded injectivity radius, meaning that the injectivity radius at each point is bounded by some constant. And the second condition is that this space has finite volume. Okay. So we also have a version for semi-simple groups that are products, non-irreducible high rank symmetric spaces, which are products of rank 1 spaces or other spaces. But the statement is not as clean. So let me stick to this version, and I encourage you to look at the paper for the most general version. It's a little bit more technical. Okay. So now I did mention this is related to Margulis Normal Subgroup theorem and why. So let's see how it's related, and I will also see some counterexamples in rank 1, and that explains why the higher rank assumption is needed. So the normal subgroup theorem is a celebrated result of Margulis, which says that if G is a higher rank, semi-simple, So in this case, we allow products of rank 1 groups, and gamma is an irreducible lattice. So irreducible lattice in G, and normal subgroup of gamma then the conclusion is that then either n is a finite index or n is actually in the center of gamma. So it's finite and central. So this was proven by Margulis. I don't really remember when, probably 70s. And the proof is quite beautiful. So Margulis shows that the quotient of gamma by n would have to be at the same time amenable and have property T. Of course, those two properties together imply that it's finite. Thus, we have this conclusion. Now, why normal subgroup theorem has anything to do with our result? Well, it turns out that if group G, which is the isometric group of this locally symmetric space, has a lattice which admits infinite index normal subgroup, this is automatically a counterexample to theorem A. So in this sense, theorem A is strengthening of Margulis normal subgroup, at least in the setting of simple groups G, because for other groups, I would have to explain this more complicated statement of the theorem. So let's see. So let's assume gamma is a subgroup of G, is a lattice. And n is a normal subgroup of gamma. So n is normal subgroup of gamma with infinite index. So I can make here a remark that by a theorem of Delzant, if G is rank 1, this is always possible. So we can always find such a group. So even for rank 1 groups that display some kind of superrigidity, Margulis normal subgroup can fail, and they will have those normal subgroups of infinite index. It's kind of interesting thing. We can always find such a group. I think this is a paper from 99. I might be wrong. Delzant, probably published in Duke. Okay, it's a nice paper. More than that, he even shows that this normal subgroup can be made free, and the quotient can be made hyperbolic. So this is very strong. Okay, but back to the main topic. When I have such an infinite index normal subgroup n, it turns out that the injectivity radius on the space x mod n is always bounded. So to make the proof easier, let me assume that gamma is a co-compact lattice. Right, so why this is true? So let's see. I will introduce a new piece of notation. So let's say that injectivity radius of the whole space is by definition determined, is by definition the sup. Right. Sup p in x mod gamma. Actually, I can put here anything. So del some lambda injectivity radius at x. So I have to warn you that this is not standard notation. Some people, when they write it, might mean infimum, but for the purpose of this talk, let's adopt this. Right, so if n is normal, then I claim that if so let's choose a compact fundamental domain for the big group gamma, and then I claim that the supremum of the injectivity ready in the quotient x mod n is already achieved on the set F. And this should be clear because the group n acts by isometries on the space x mod. Sorry, the group gamma acts by isometries on the space x mod n, and the fundamental domain of this action is F, is the image of F. But if you have a group that acts by isometries, this action must preserve the injectivity radius. So that's why the supremum of the injectivity ready is already achieved on any fundamental domain of this action. So that's why you can take F instead of x mod n. Okay, so yeah. So this is compact. So this thing must be finite. Okay, and that's the proof that those kinds of spaces will have uniformly bounded injectivity radius. So a corollary is that theorem A formally implies Margulis normal subgroup theorem. So now maybe I'll give you a few, say something about history of this problem. So apparently Margulis was thinking about such a statement for quite some time. Partly he was motivated to return to this question by the paper of 7 authors on Benjamin-Duchamp convergence for local symmetric spaces. And he asked this question. So whether this is true that infinite injectivity radius implies infinite volume implies infinite injectivity radius. And fortunately with Tsachik, we were able to solve it very recently. Okay, so yeah, I think I gave you I explained what we proved. I explained the relation with the normal subgroup theorem, and also I explained why it doesn't work in rank 1 groups. So now let me maybe give you a very brief outline of how we prove this thing. And if I don't manage to do this in the scheduled time, I'll continue on my next talk. So idea of the proof. So our first step is to translate the statement about local symmetric spaces into a statement about discrete subgroups of G. So to do this, we'll introduce the Chapotis space of subgroups. So probably there are other talks on IRSs which must mention this topic. So if you want to learn more about Chapotis space, you might want to listen to those other talks. So Chapotis space is the space sub G. And this is the space which consists of closed subgroups of G. So it's a space whose points are H in G. H is a closed subgroup. And this space is endowed with topology of Hausdorff convergence on compact sets. Okay, so the group G acts on sub G. So it acts by conjugation. Okay, and there is a way, now there is a way to translate the statement about injectivity radius of a local symmetric space into a statement about orbits in this action. So here's, I'll put this translation in a box. So a space X mod gamma has infinite injectivity radius. This is equivalent to saying that the orbit of gamma in sub G contains the trivial group. So that's the translation. Why is this true? So actually, well, if you look back at the definition of injectivity radius, so if P is a point in the space, in my local symmetric space, so P is a gamma, I don't know, sorry, lambda GK in this quotient, then it turns out that injectivity radius at P is bigger than R. There was this condition of Ball, but we can translate it as follows. So this actually means that for every lambda in lambda, if I look at the well, let's exclude the trivial element. If I look at the displacement of my point X by lambda, this must be bigger than R. So this is direct translation of the condition about injectivity radius. Right, so and I think it's not hard to see. So you can verify that for yourself. And now I can just do a simple trick. So instead of putting gamma here and X here, what I can do is I can go to, instead of working at the symmetric space, and I can pull back this metric to G. So this is metric in X. I can pull it back to G. And now I can look at the what. So this would say that, sorry, this should be X, but P. Yeah, P. And this would say that displacement gamma, distance from gamma, sorry, lambda G to G is bigger than R. But then this just means that distance in geometric from the conjugation of lambda by G from 1 is bigger than R. And this holds for every lambda in big lambda without identity, for every lambda in big lambda without identity. So the condition on big injective radius means that for every conjugate of lambda by energy, you don't see elements which are closer to R to the identity. And now, since this injective radius is supposed to be unbounded, this means that you can, in this local symmetric space, you can find points P with some G, where this radius is arbitrarily large. So this means that you will find a sequence of G's such that this will grow to infinity, and therefore this will go to infinity. So in other words, this sequence of we can translate it back into a statement of subgroups. So this sequence of subgroups. Let me just write it that this produces a sequence of conjugates lambda G with which tend to trivial subgroup in the Chaboti topology. Okay, so I'm very close to being out of time. So this translation, nothing much happened here, but what we'll do next is that we'll prove some facts about dynamics of this action of G on the space of subgroups, which are both fall under the territory of, I guess it's, you can say that it's measured group theory. So because of higher rank, we'll be able to exploit some magical theorems, rigidity theorems, which will allow us to kind of classify the stationary measures on this space. And thanks to that, we'll be able to classify the closures or say something about closures of orbits in that space. And when we translates our statement back from sub G to something about locally symmetric spaces, we'll get exactly the statement of theorem A. Okay. And this part didn't use higher rank yet, so this will come next. So I guess that's it for this talk, and see you in the next.